moving from there, we will now come to shear force and bending moment diagram. And so this is going to be a precursor to stresses, right? We are mainly interested in stresses in this part of the course, because once we know the stresses in an element, we can then design it for diameter, length, and so on. Okay, so let's get to shear force and bending moment diagram. So the question is, what is a shear force and what is a bending moment? Okay, when it comes to beams. So take an example of a beam which is simply supported. Let's put a roller on one end and a pin joint on the other, and load it with a force, a concentrated load P. Okay, and so for a problem like this, we can draw a free body diagram like this. At A, we have a roller joint, so that roller will induce a vertical force only. At B, there is a pin joint, so that will induce a vertical force as well as a horizontal force. And then, of course, P is a external load.
Which should that be HB?
Yes. Good catch. Okay, so far so good. Now, as I said, we are trying to get to stresses, and the way we get through stresses is through shear forces and bending moments. So what we're interested in is perhaps the design of this beam, and we want to find what's going on at a cross section of the beam. Okay, so if we cut the beam right over there at the line I drew there, then you would have something like this, right? So that's the cut. Now, this is the system as it would be when the force is 0. So no P. If, however, there is a load P, what you expect is that the beam will actually sag. So if there's load B, then it will look something like this. So what will happen is that load P will cause a force which will manifest itself over here. So that force, which is not P, but it's a different force, okay, let me call that force V, and this is V2. We'll note how I drew V. I drew V downwards on the left side, upwards on the right side. It could well be that the force is reversed, right? It could be upwards on the left side and down on the right side, doesn't really matter. That we'll get once we solve it. But let's assume there's a force. Important thing here is that this force V is equal and opposite on the right side because, again, this is a free body diagram. So if we cut it, the force appearing on the left side, it should again appear on the right side because when you join the things together, the force disappears. It should add up to basically 0. Okay, so this force V is the shear force. Okay, and in this case, actually, it turns out that the shear force is actually equal to P, but well, it's half of P. But in general, it has to be computed by us in a problem involving a beam so that we can then use it to do other calculations. So that shear force, if it is increased, if V is increased, okay, we can increase V by increasing P, then the beam will eventually break at the cross section okay, and we say that it breaks by shear. The shear force. So clearly shear force is important because it will cause the beam to break by shearing. By shearing, I mean it's going to slide. One face on the right side will slide against the face on the left side. That's the shear force. Now there's another thing which is going on here. If you see the beam in our experience is going to bend a little bit. Okay, so I'm going to redraw the beam. Okay, now there's no cross section, but I just isolated the beam under the load P. So it's common experience that the way this will bend is the inner part, it look like it curves, right? And if it curves, then we can say with certainty that the top part of the beam is under compression because its length has decreased compared to its length when it was not loaded. And the bottom part is actually up to that the line I drew there. And then the bottom part, this one, is under tension. Okay, so if we have a beam which is now bent in the shape of an arc, then we can say that it's actually being bent by a moment, bending moment M. So clearly there's a bending moment involved. If there was no bending moment, it would not have bent, right? So the problem here, which involves just a force P, will lead to two things. One is a shear force at a cross section, and the shear force will be a function of the length, and it will also lead to a bending moment. Now, in this case, I've shown you M. I just said M is the bending moment, but the bending moment actually is going to change as a function of distance because in this case, well, it's because there's a constant load, the moment is constant, but if there were multiple loads, then the moment actually changes as we go along the length of the feet. So those moments and forces are things we want to find because they are related to the stresses which will be generated in the beam. And those stresses are important because we design the beam based on the stresses, which are then related to the stress strain diagram. So in this course, we will look at a few types of forces. This might be a review of mechanics of materials for some of you. So we have three types of forces. We have the concentrated load. And I just drew an example of that, a beam subjected to a load, let's call it F here. We have a distributed load. So that normally is drawn in the form of a couple of arrows and a over bar, and it's denoted by the letter W, small w. And then we have the last one is a moment. So here we have a beam. Under the same loading condition, so same supports subjected to a moment. And now that moment can be really anywhere. So there are a couple of formulas which you should know about, and these are sort of going to be important when we talk about shear force and bending moment diagram. The first one is how the shear force V is a function of the moment. Okay. Normally, what you would usually do is you say that the moment is force times distance, right? And so it's really a manifestation of the same formula, except that you write the distance as a dx and m as a dm. And so you have the force is v in this case, distance is dx, and that's known as dm. Okay, so that's one formula. So just to help you remember it. Then there is force per unit length, that's dv dx. So this one is an example of a force that is distributed over the length. So W, for example, is dv dx, but I would like to use Q as a general variable for force per unit length. And so then if you use this formula previously, V equals dm dx, then you can write d square m dx squared, which is the second derivative of the moment. And then finally, if you want to use this equations, so let's say that you know the moment. I give you the moment here. It's known. I told you to find the shear force. Then you can actually use this formula to find the moment. It's going to be dm equals v dx. And typically, you want to look at 2 points, say A and B, some random points on the beam. So you'll integrate from A to B. And similarly here, the integral is usually over the length. So it's going to be x A to x B. And you could do the same thing with Q. Q is force per unit length. What is it called in the book? I forget. I'll update the notes. I kind of blanking on what it's called. It's called something. Somebody remember the knows, let me know. I'll update it later. Shear load, maybe it's called shear load. Let me put that in. So I'll verify it. My notes would be updated with the correct name for it. So now I'm going to integrate Q dx from XA to XB. There's a lot of clutter here. Let me get rid of this. And I really would recommend that you don't really have to remember everything. I think if you know this formula, those two formulas I put in red, you should be fine. So here is my recipe on how to draw shear force and bending moment diagram. And we'll just use this to find the shear forces. And we'll do two problems which will illustrate this. So how to draw shear force, bending moment. Okay, by shear force diagram, I mean V as a function of X. And by bending moment diagram, I mean the moment as a function of X. That's the shear force diagram, the bending moment diagram. So first step is draw a free body diagram, which you've already seen in the last class. Second step is to compute reaction forces and moments at the support. Forces and reaction moments at the supports. Okay, this is something we've already done. How do we do it? Well, we use the equations. Summation of force in the x direction is 0. Summation of force in the y direction is 0. Summation of moments about any point is equal to 0. Okay, so the last step, which is the shear force bending moment diagram, and is as follows. So find the shear force, okay, and bending moment at every location of the beam using the equations P equals dm dx and Q equals dv dx. Okay, now it seems very tedious to do that for every location, but turns out that you really don't need to do it at every location. You can actually do it at strategic locations, because you will see, as you see, that the bending moment changes whenever there is an external force V, and the shear force changes when there is a distributed load Q. So as long as the moment you see that change in the free body diagram, that's when you'll apply these equations. So you will not really do it for every location, but you will do it judiciously, and you'll probably use that formula maybe 3 or 4 times, depending on the load. So that should become clear when I do some problems. So I said every location in principle or in practice you only need to use these formulas at a few locations wherever V M changes. This will become clear, as I said. Now, one more step, and then we are ready to start solving problems. There is a sign convention we'll follow. We've already seen a sign convention for the reaction forces, right? We drew the x-axis, y-axis. Positive is usually to the right, and positive on the y-axis is upwards, and then counterclockwise positive for m. But we also need a sign convention for v and m, and so the sign convention we'll be using is pretty much used for in most of the text. The sign convention is as follows. So this is for step 3. So when we'll be drawing shear force bending moment diagrams, you will be cutting the beam at various sections, right? And so when we'll draw the free body diagrams and we'll be cutting the beams, we'll either move from left to right or right to left. So if you move from left to right, you will be using, let me just put cut. So here is a beam which is cut, let's say in the middle. And we can look at the section on the left side or look at the section on the right side. If you want to go from left to right, what you would do is we'll assume that V is positive downwards and M is positive counterclockwise. Okay, and on the right side, you would have V positive upwards and M positive clockwise. So it's up to you if you want to go from left to right or right to left. And you'll find that using this convention, you'll get the same free body shear force and bending moment diagram, no matter how you start. Okay, so let's get started with a problem. So here's an example. Okay, so a beam is subjected to loads of 15 kilonewton load on the left and a 6 kilonewton load on the right. This is 2 meters, 2 meters, 2 meters. Let's give it names. Let's call this point A, this point B, And then the question is, draw the shear force and bending moment diagram. Okay, so I'm going to follow the recipe I put down there, those 3 steps. Step 1, free body diagram. So we have a pin joint on the left, so it would have a vertical force at A, and the convention is this is X, horizontal, Y is upwards, and we have a horizontal force at A, and then we have only a vertical force at B. Then 15, okay, and 6, I'll not put the units, but it's just going to be cluttered, so I'll just skip the units now. The second step is find the reaction forces, which in this case are 3 of them, HA, PA, and VB. So let's invoke the equations of static equilibrium, which are summation of forces in the x direction is equal to 0, which will give us HA equal to 0. Summation of forces in the y direction is also equal to 0. So in this case, we would have VA upwards is positive, so it's positive. VB is positive, which is upwards. 15 is a force acting downwards, so minus 15, and 6 is downwards. So this gives us VA plus VB equals 21. Okay, and finally, I need to find, it's like 4. So finally, I need to find the forces V and VB. So I'll use the moment equation, and I can use the moment equation about any point. Usually it's recommended that you use it at a point where there are most number of reaction forces. So you could use it at A, but here we know that HA is 0. So it really won't be any less computationally expensive than doing at B. So, but let's just use A. MA equals 0. So that gives me, so moment about A. So we have, well, the moments due to HA and VA are 0 at A. So we only have to find the moments due to the 15, 6, and the force VB. Remember that this is 2 meters. This is 2 meters. This last piece is also 2 meters. So we are all set. So let's write the moment due to the force of 15 kilonewtons. I'm going to skip the units. It's actually, I should have written 15,000, but I just skipped the kilonewton. But remember that the forces which will come out of this are going to be in kilonewtons. So 15 is acting in the direction shown about point A. It'll induce a moment which is this way, as shown, it's clockwise. Clockwise is negative. So negative 15 times 2, 2 being the distance from A. Next, we have the 6 kilonewton force. It's acting at a distance of 2 plus 2, 4 meters from A. And it's also inducing a clockwise moment about point A. So it have a negative sign. And then we have VB, which is acting at a distance of 2 plus 2 plus 2, which is 6. And VB induces a counterclockwise movement. So it's going to be positive. So this whole thing is equal to 0. And we can use this to solve for VB. Comes out to be okay, so VB is 30 plus 24 divided by 6. Is it 9 kilometers? Substituting in 1 gives me a VA, which is 21 minus VB, which is 21 minus 9 is 12. Okay. Okay, so the last step now is shear force and bending moment diagram, which is probably the most involved part. What I'm going to do is, the best way to do this is to draw the beam and then just draw the shear force diagram just below it, so it's easier to visualize it. So I'll do the computations and everything on as I basically draw the diagram. So it's really up to you how you want to do it. Some people like to do it in a different place, but I think for explanation, it might just be easier to do it the way I'm doing it. So draw the beam. And then show the forces, the reaction forces as well as the external forces, 12 and 9, and then 15. And 6. Yes. Okay, so what I'm going to do is, and if people who are writing on paper might find it hard. I can actually draw it and move it around, but I think if you're writing on paper, you will not have this. Okay, let me just do it this way. How it will be eventually. So the goal here is to find the shear force at every location. As I said, we can do this strategically by choosing a few locations. So the way this works is every time the force changes, the external force changes, you need to write an equation. So what I need to do is I need to write a shear force equation here, here, and here. That's it. So three equations. So let me draw those here first. So I will draw a cut. So I cut the beam exactly where I showed. So I just do that part. Then I'm going to cut it right there, the next piece. So it's going to be here. And then I'm going to cut it there. So it's going to be something like this. Okay. And so my shear force diagram will probably come right below the last one. Let me draw the axis. So this is going to be my shear force as a function of x. Okay, so as I said, what I need to do is write the shear force equation, V equals dm dx. Back. So I need to use this equation for shear force. And I need to use this equation for bending moment. Okay, and I'll basically use the integrated form, which is dv dx, dv equals q dx. So that's 12 upwards. Again, we go back and I'll show you the convention. Since we cut the beam on the left side, our shear force downwards is positive. So I go back and show a shear force in the downward direction with a positive sign. Here Q is 0, right? There's no external load, distributed load. So really what I need to do is I need to just sum up the forces. So I can write for this part plus V, because that's the downward direction is the positive direction. Upward direction is negative. Okay, do not confuse this with the Fx, Fy for the reaction forces. This is a different convention from that. I'm using the second convention for the shear forces, which I wrote down here. See, this is the convention I need to use. Positive is downwards if you're going on the left, and it's positive if you're going, positive is upwards if you're going from the right. So I'm using this particular convention. That is, I'm starting for the shear force from the left to right. That's why I'm using the convention shown here. So V minus 12 equal to 0. So then V equals 12, which means that all over here from the left up to this mark, the red first red dashed line, the shear force is going to be positive 12. So I just need to draw it here. Okay, it's going to be the same for the entire section, because between 12 and 15, all the way just slightly to the left of 15, there's the only shear force is because of the reaction force 12. So it'll stay 12, and I do not need to compute that at every location. We'll do it a little faster now. So now we have this. Let's redraw the forces, 15. And now again, let's stick to our convention. V is positive downwards. And so I can write now positive V minus 12, because 12 is upwards, 15 is downwards, equal to 0. So V equals, it's minus 3. So exactly where the 15 kilonewton force acts, the shear force changes from 12 to minus 3. So it goes down, and right here, it's minus 3. Okay, this is a V is in kilonewtons. You can just put it as V kilonewtons. Okay, so that completes the second equation. Now let's go on to the third one. So we have 12 upwards, 15 downwards, 6 downwards for the next section, and then V is downwards per our convention. So now we can write the equation here, plus V plus 6 plus 15, because all of them are in the positive direction, and positive is downwards, minus 12 equals 0. And if you do the math on that, it comes out to be 21 minus 12 is 9, and so it's positive 9. It's negative 9, sorry. Good catch. So that means that the force is So it's 3 all the way here, and then it jumps to -9. Now you could write another equation for the piece just after the 9. You will see that the shear force there is equal to 0. That's because that 9 kilonewton acts upwards. So it will actually close down here. It'll become back to 0. So it starts off at 0, ends at 0. So that is the shear force diagram. Okay, maybe clean it up a little bit so it's much clearer in my notes. Move this a little down. Okay, so once I get rid of the lines, it will be a little bit more clear. Okay, any questions on this? So you'll be a little bit patient and just follow the rules, and it's pretty simple to draw these diagrams. So let's draw the bending moment diagram on the right side. The only reason I want it on the right side and not on the next page is because I'll actually, sometimes it's useful to have the shear force diagram besides it so that we can use that to accelerate drawing this diagram. So bending moment diagram. So let's draw the beam again. Okay, the philosophy is the same. That is, instead of drawing this for every location, you strategically draw it wherever the shear force changes. So let's look at this equation here. So we're going to use this equation. Okay, we're going to use it wherever those locations are determined wherever V changes. Okay, what is V? V is the shear force, and shear force is on the left side of this figure. So we notice that our shear force, it changes here, and that's about it. It's here, 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 and here, if you like. So we just need to draw diagrams for those. Well, you to draw similar figures just like this, but one just before that, one over here, and one over here, exactly like the previous one. So let's just do that. So here is this is a helpful. Okay, let's draw the same element. Same element here as on the left side, and then again. Okay, so what we need to do here is put the shear forces as well as identify the external moment. So we have V and we have M. We need to put V because this V induces a moment. So we actually don't need it. My bad. We just need to put the moment. Okay, so what we do is we use this equation, V equals dm dx. So dm is V dx, And so if you want to find the moment, it's going to be, and the moment is about this point. Okay, so about that point, we would have, and let's say that this is the distance x from 12. So this moment is by convention positive. If you turn a page, you'll see that the moment on the left section is positive when it's counterclockwise. And this 12 times this distance x produces a clockwise moment. So you'll have minus 12 times x. So when we draw the bending moment diagram, we'll use this equation now equals 0. So m equals 12x. So we know that x changes from 0 all the way to, in this case, it's 2. So the moment starts 0. It increases to x equals 2. So that's going to be 24. Move to the next section, 12 m 15 downwards. Okay, so now what we'll do is we'll say that this distance is x, and we take moment about this point, the same point at which we took the section. So m is counterclockwise, 12 is clockwise, and then 15 acts at a distance of, this distance is x minus 2, right? Because the length from 12 to 15 is 2. So we have 15 times x minus 2, and the sign there is going to be 15 act produces a counterclockwise moment, so it's going to be positive. Okay, let me write the equation for this, and then I would like you to fill the dots. So let me just write the equation, and I want you to figure out, I'll draw the bending moment diagram, but I want you to figure out this yourself, but I'll put the equations down. So here is 12, 15, and then 6. So we'll have m counterclockwise. This is going to be x. So minus 12x. So 15, this is 2 meters. That's 2 meters. So it's going to be x minus 4 with a plus sign because it's going to produce a counterclockwise movement. And then the 6 kilonewton will produce a force which would be x minus, well, this should be x minus 2, because that's x minus this 2 will give me the distance from 15 to, this distance is x minus 2. And then x minus 4 similarly equals 0. And then when you, okay, I'm going to clean it up a little bit later. So when you see the notes, it'll be much cleaner. But then the free body diagram, so the bending moment diagram will look something like this. Where this value is 16. And then it goes to 0. So it's just a matter of chugging in the value for x. So you'll put x equals 0 to 2, then you'll put 2 to 4, and then 4 to 6, and you'll get the diagram. So I'm going to clean it up so it won't look this cluttered. And next time, and actually I'll also post another problem in this notes. So if you want, you can work it out, and I'll do the solution in class on Friday.